Next up is Lindsey from Gigamon. And we had discussions of namings earlier. So Lindsey, I went and asked every woman in the room on the first day if they were Lindsey. And then I looked him up, and InfoSec people don't have many photographs. So there was one photograph of him and his partner, who turns out to be called Lindsey. So at that point, I gave in. Found him eventually. And he's going to be talking today about multi-stage classifiers. Thank you.
Thank you. So it's true, my wife's name is Lindsey. And when we started dating, she thought this will never work, but can't always predict. So before I start, I just wanted to very quickly, I'm the last one, and as an attendee, I just wanted to express my gratitude for this conference. I did go around and I polled some people about what they really liked about the conference and got some input. Very professional, very professionally done. Coffee was awesome. Like the fact that it's collaborative, small, and with no sales. Great venue, especially the comfy seats. And also, I especially appreciated the dystopian alleyway entrance that gave us a glimpse of our robotic overlord future. So with that, I'll get into multi-stage classification. So the first thing I'm going to do is just let you read this slide, this conversation. So this is completely fictional and exaggerated, but I think there's a little bit of truth in it. I've noticed that often when you have big systems produced by many people, you might have your classification engine, but the thing feeding it might have some type of filter based on heuristics. And just this general problem kind of is what motivated me to look at this type of problem. So multi-stage classification is also known as cost-sensitive classifier. So a cost-sensitive classifier, just to give you some examples that are not cybersecurity related. One is photo detection. Here's an example of Google Lens. When they started out, what they would do is they would take the photo and they would ship it to the cloud in order to do the object detection and then ship it back. In medicine, not only do you have the monetary costs of doing diagnostics, but you also have the health risk associated with any diagnostic. And in that case, it's very important to try to reduce the cost of the initial stages of diagnosis. Also in physical security, although maintaining a high level accuracy is ultimately important, you still have to get passengers through the system. So there are requirements there as well. So these are some other examples of cost-sensitive classification. So there's a general framework. I like to use the mobile phone object detection use case to kind of go through the framework. There's a general framework that's been built for multi-stage classifier. You have the brain in the cloud, which is kind of represents your primary classifier. It's the one you might use if you weren't dealing with a cost-sensitive scenario. And then you have the small brain, in this case on the phone, and this has two functions. One function is to decide whether to pass it on to the main classifier and incur some of those costs if there are any. And the other one is if it decides not to pass it on to the main classifier, it classifies it itself. So here's some examples of some of the costs that could be associated with this overall framework. Right? You could have costs associated with the sensor acquisition of data. You could have the memory. You could have the pre-processing cost. You could have the model evaluation and model storage costs. And then you could have the transport costs. If your primary classifier is remote, you'd have to transport it there, and then you'd have all the costs associated with it before you can make your final classification. Now, this isn't limited to kind of a remote scenario. You could just picture this as, hey, I want to make the things in my box higher speed, and I have some costs associated with my primary classifier, so I want to speed up my box by having this front-end stage that can short-circuit the decision. And also, it doesn't have to be a single phase, right? You could have multiple stages. So let's look at this from the cybersecurity example. So the objective I took on in this research was to develop a distributed malicious file classifier that minimizes costs while maintaining overall accuracy. Some of the constraints I was looking at, so some parts of the research of this research area are how to compress your classifier to both save space and make it faster. I kind of put those to the side, and it was mainly looking at the parsing cost, the model runtime cost, and the transport cost, assuming a distributed classifier. Also, I used the Ember dataset. It was very helpful to have that available to use it at a moment's notice. The other thing I did was I wanted to take out the confounding influence of using different models. So I decided to just use a deep neural network with 3 hidden layers, 256 nodes per layer, just a basic, wherever I could use it, that's the model I used to try to, because I was focused on some of the strategies as opposed to the model itself. So one of the initial things when I started to investigate this data set, one of the initial things I found was that parsing costs are actually quite significant when compared with some of the other things. So like model runtime was a fraction of even the smallest subsection of the parsing. And the transport time was about equal to the overall parsing costs, but that wasn't a huge surprise. And what this graph shows is each of these bars, the Ember code has different sections that produce the different feature vectors. So the one exception in this case is the LIEF, the leaf. That's a library that does PE parsing, and that's kind of a prerequisite for the others. You can see that's kind of a middle size. But all the others create feature vectors, and you can see they have different costs associated with them. So I got these times based on running it over like 40,000 PE files. I kind of took it as a constraint that I wanted to keep these sections intact, right? So a lot of the cost-sensitive classification research, it assumes that you could look at an individual feature. And if I looked at all of the features in the entire feature vector that Ember produces, I didn't want to pick out just one. I wanted to pick out a section, so that because sometimes it doesn't make sense. Like if you're looking at the histogram, right? It's the same work to produce the entire histogram as to pick out, one of the constants. So here's the overall cost structure I did. The cost points are kind of arbitrary, but they're kind of related to time. So you can see the cost groups, and then you have leaf, the prediction is nothing, and then the transport. And I assign cost points to each of those. And when I was looking at evaluating kind of my overall results, I'll show you this graph. You can see the static neural network accuracy score at the top is the line across the top. Vertical axis is accuracy, and you can see it only goes between 98 and 94. And the cost per sample is 0 to 300. So 300 would be sending everyone back to the primary classifier. So you can see that dot in the upper right is kind of the best accuracy but worst case cost. And the objective is to get as high and to the left as possible. So some of the initial experimentation I did corresponded with some of the early research I had looked at in this subject area, and it's a little bit intuitive, and you'll see what I mean. So the first experiment I did was I made a low-cost filter, a low-cost classifier. I took the 2 lowest cost feature groups, and I created a classifier just with those 2 feature groups. Once I got the results from those, I just did a filter that rejects the negatives. So for an arbitrary threshold, anything that was negative, I said, the classifier is going to say this is negative, and I'm going to pass everything else back. You can see the yellow is forward to the next stage, so anything over the threshold, I'm going to send back to the primary classifier, and I'm going to assign the value that it says and accept that cost. So when you graph this, you see, okay, I've cut my cost about in half, but if I go too far, the accuracy really falls off. So maybe it would be acceptable to have a slight degradation in accuracy at half cost. That's what I have with this first experiment. So the next experiment I did was, if I'm highly confident that some of the negative samples I can just assign right away, I'm going to assume the same thing about the positive samples and just have the middle section forward to the next stage. So you can see we do even better here, right? We save much more on costs. And a lot of the research, the kind of early research in this area was about how to choose these thresholds. These experiments are just showing kind of what the optimal values I can get for those thresholds. The next thing I did was a just slight variation on that, where I say, well, I'm gonna make the thresholds so they don't have to be symmetric, right? So I'm gonna just scan over all combinations of the two thresholds and see what I get. So in this case, it's the green line. It's very similar to the dual thresholds. It's slightly better on some of the lower accuracies, but very similar. So at this point, I started to get, I struggled to do much better. So in this case, I was trying to figure out, basically, if I could establish, at this point, I wish I had some of the research that Rich had worked on, because this is exactly one way to address this problem. There's two things I can do. I can either change the features I'm using, or I can have a better confidence about what samples I really know are positive and which samples I really know are negative. If I had that, then I'd be able to do better. So in this case, this was kind of a, I basically was trying to predict which samples would be problems and try to push those towards the middle of my confidence range, and it totally failed. It was much worse than either of the other previous things that I did. On some earlier sample data sets, I had tried to do some Bayesian deep learning to try to establish a better confidence, but in my earlier samples it didn't work, so I didn't try it with this particular data set. So at this point, I did a more comprehensive review of the literature, and kind of worked through what was more recent and possibly would be more successful. Two recent papers stood out: one by Janish and one by Nan. One of these had to do with deep reinforcement learning as an approach. The other was basically both of them were working on jointly modeling cost and performance. At the time each was released, they both said they were the state-of-the-art results, and a big pro, even though it was research code, they at least had code associated with the papers. Much easier to deal with code than trying to re-implement the paper just from the paper. The adapt GBRT approach was a boosting tree-based approach, and that essentially searches for the fixed set of features that could be used in a low-cost classifier that would fulfill this objective of optimizing for both cost and accuracy. The classification with costly features one was a reinforcement learning approach. It used a deep neural network as the brain. Specifically, it was a double deep Q-learning network. And it treats revealing the feature sets as actions. So it either chooses a positive, chooses a negative, or chooses to reveal another feature. Here's the benchmark results. You can see the red line is the one in common between the two, so that the classification with costly features was a little bit better. And that's the one I chose to go with. Not only, well, one, because reinforcement learning is kind of new and cool, but also it was fairly straightforward to modify the code to account for the feature groups as opposed to the individual features. And it was also flexible, so I was able to say in the action space of the reinforcement learning, either positive, negative, or send it off as an actual action, or reveal one of the feature groups. I'm not going to go into much detail about reinforcement learning, but basically this algorithm is very similar to the algorithm that DeepMind introduced when they revealed that they were able to play video games, and there's a big example of having it learn how to play Breakout and learn that, you know, the best strategy is to hit the ball around the corner so that it bounces along the top. The three components that I built into the code, that were in the code, were experience replay target network and double Q learning. You can look at the details of this, but essentially those are the three pieces that really made it successful on the early video games that it was able to learn. So those were a part of it. And I modified the actions, as I noted, to be the feature groups, and then a positive, negative, and a 0. So the results look pretty good. It's the purple line over here in the left, and you see I have gotten past the simple kind of threshold-based approach, and it did successfully optimize for both cost and accuracy. You can see here the kind of one of the dots I see as optimal. There was a 0.1% decrease in accuracy at about less than 1/5 the cost. There are also some interesting insights when I looked into some of the things that the reinforcement learning neural network, the decisions it was making when it was doing the classification. So it always looked at the header section first, and then I've kind of weighted the paths that were most popular in the final model on the test run. And you can see the most popular one is the header, and then the histogram, and then deciding that it's a negative sample. And these are just the top 8 decision paths that it took, with the addition of the very top reject, kind of send to the next primary classifier. I mapped out, and you can see that it checks many sections before it rejects it. And because it was trying to reduce cost, it only, you know, the number of cases it would do that were much smaller. So in the spirit of not always having super positive results, remember how I said that I decided to work just in the space of one type of model, which is deep neural networks. If you actually just use the light gradient boosted machine model that's comes standard in Ember, if you do that with this, you actually, because it's a higher accuracy than the deep neural network overall, you get a higher line on the right, and it also does better even with only a few features, so it kind of raises the whole graph up and makes it competitive even with the fancy reinforcement learning-based neural network. So, different data sets are going to work better with different models, and so this is a case where one of the lessons learned is it's important to establish the type of model that works with your data first, because that's going to be something that's hard to beat, even if you have this other objective of optimizing for cost and accuracy. Also, in general, I found these cost performance optimization tools very interesting, and Right now, they're kind of there's only research code, and there's not. It's not like there's a plethora of different types of models that you can use. So in the future, if this area became more popular, it would be nice if it supported different types of models as well. Also, the reinforcement learning, I was pleased with the overall success of it. It's a little bit fidgety to train, but I thought it had very interesting results. So for future work, future areas I could see investigating would be reinforcement learning. Most reinforcement learning methods are all deep neural network based. There's no, I've read things saying there's no reason they couldn't be other things as well. Reinforcement learning is a very active area, and this was kind of one of the oldest successful ones, so there's a lot more that could be explored there. I'd like to test the modification of the adapt GBRT to see if that would be successful. And also there's the idea of, because of the high parsing costs, maybe some raw features could be used to bypass the parsing need as a part of this type of model. So the key references are the Ember paper and those two papers I mentioned. Any questions?
Here's this one. No, you're going to need that one. Is it on yet? Sweet. So thank you again, and I guess we start the questions with, this looks pretty damn useful. So is it worth adding in its current state into some of the machine learning libraries? Is it ready? How much would it take?
Yeah, so the reinforcement learning piece in particular, because it's under such active development, and also because, so the implementation I had was easy because I was kind of simulating that, if it wanted to see another feature vector, it would go run that code. That isn't totally integrated right now. The adapt GBRT model, I could see as being something you would want to add to scikit-learn, because it does just go through once and select the optimal set of features. It's very much like a feature selection type routine, so I could see developing something like that into yeah.
So if we have a kind of a contrarian example, right, of two features, one cheap, one very expensive, but it turns out the problem's just XOR, right? So it's a terrible idea for us to actually run a cheap version, because the XOR problem is like, it's problematic. Does your framework, or I guess you would see it in like kind of loss of accuracy potentially, but do you envision like a testing to show that no, you really shouldn't do any kind of low cost version of this model at all, because your problem is very sensitive to this, and it would be a bad idea?
Well, there's no reason why any type of cross-validation you can't do with this problem. So I think you would know from that. I did find that it was interesting that some of the early features that the model did decide to use were expensive ones. So yeah, I think the main answer is, cross-validation type testing works with this, so you'll know whether it's something that's not feasible or not.
So I really like the idea, but so I know you said in the beginning that you were going to keep one model and then put the cost on the features, but have you given thought to putting, like, if we had a gradient boosted tree that's cheap and a deep learning model that's expensive, like, have you given thought to switching that? Like, how would you do, what would you do, having thought about this process?
So that's a good question. I hadn't thought about actually changing the model midstream. Certainly something you could do. In my particular work through of this example, the actual runtime was not the issue. So if you would be swapping models in order to kind of improve runtime, that would probably be a different type of situation than this. Certainly, I think there's still a lot of open space in kind of how this should be implemented. The adapt GBRT, actually in both of the papers, they mentioned, hey, we could try this with different models. I don't think any of that settled.
No more question at the back.
So could you say a little bit about what the state space is that you're searching over?
Yeah, so he asked about the state space that I'm searching over. Maybe I'll go back to this line. So in the literature I referenced for these two models, the state space they were searching over, I think they used the canonical forest cover data set. It was one of their bigger data sets, and I think the CFAR. So they did have pretty significant state. In my particular experiment, because I used the feature vectors, I suspect that it really reduced the state because I'm only searching among these 8 options in addition to the 3 kind of plus, 1, 0, or send on. I think it was probably a smaller state space. But the reinforcement learning in particular, the state space was probably larger as in most reinforcement learning situations because it was searching all combinations of, each time it revealed a feature, it was kind of a new type of thing it might see. So there was still probably a lot of state there, but I did reduce the overall number of actions that it was looking for. Does that answer your question?
That's what I'm trying to understand was, is it just presence or absence of each of these categories? In which case, maybe it's not that large a state space to do a more kind of broad search to figure out the split.
So to be clear, it was. So he was asking whether it was just is this thing present or not type state space search. And to be clear, if it goes through here and it says, I'm going to look at the header, then in choosing its next action, it has access to the header feature vector only. And then it has to choose 1, 0, or reveal some new feature vector. So then if at that point, if its action had said reveal imports, then the next decision, it would have header feature vector and imports feature vector present, the rest of the feature vectors not present, and then it would decide, what do I want to do now? Do I want to call this positive, call it negative, send it on, or reveal another feature vector section? Does that make sense? Okay.
Okay, I think, have I not turned it on again? Thank you. So I think that's a wrap then, and thank you very, very much again, Lindsey.